Okay, we're going to begin our discussion now of the dynamics of rigid bodies. So we're going to look at them moving. We're going to look at not just kinematics, but forces and moments and energies. But we need to start off by looking at the concept of moment of inertia. This is oftentimes referred to as mass moment of inertia. And there's a distinct relationship now between moment of inertia and kinetic energy. And how we want to do this is we want to take a look at a point mass, a very small mass for starters. So it's going to have some mass m, and it's going to move in a circular fashion around some center. So imagine this is a circle of radius r. Then I can describe the motion of that mass, if it's circular. I can describe the motion as having some velocity v, which is equal to r times omega. But if I do that, then the kinetic energy of this particle is 1/2 mv squared. But that's going to equal 1/2 mass times r squared omega squared. Now you'll notice, as we've talked about things, we have a linear velocity, and that is a counterpart angular velocity. There's a linear acceleration and a counterpart of angular acceleration. But there's a linear mass, and the angular counterpart is mass moment of inertia. And so kinetic energy, which is 1/2 mv squared, will have an angular counterpart, I, 1/2 of course, for the angular mass, and then the angular velocity, omega squared. But if you note this term right here, this must be that I term. So the mass moment of inertia of a single particle is mr squared. So I, for a small particle, is mr squared. The other thing we'll note here is that energy, whether it's linear or rotational, angular if you will, has the same units of joules. So T is equal to 1/2 mv squared, or T is equal to 1/2 I omega squared. But in both situations, the units are joules or pound-feet. Okay, so how do I calculate out the mass moment of inertia? Well, keep in mind, we've just discovered that for a very small particle, the mass moment of inertia is mr squared. So if it's really small, it's going to have a very tiny mass moment of inertia, di, and that's going to equal its mass, dm, and its tiny piece doesn't make it any difference as far as how far it is from that center of rotation. So that's going to be r squared. Or if I commute that, that's r squared dm. And so what you'll notice here is if I integrate both sides, the integral of di just becomes I, and then it's an integral of r squared with respect to mass. So that's really kind of a strange one. How do we integrate with respect to mass? And the idea is we're going to have to find a relationship between mass and position in order to do that. The subscript I0, that zero subscript, which is really an O, that's about some center point, or an origin, if you will. So that's the mass moment of inertia about that origin. Now this is not our first go-round with moments of inertia. We did these back in statics. And back in statics, we started off looking at moment of inertia. Now there's a slight difference between mass moment of inertia and moment of inertia back in statics. Back in statics, we did this for uniform thin plates. And as you recall, this was the moment of inertia that we looked at back in statics. And the idea was, if I had an x and a y axis and perhaps some shape, I'll just draw a triangle, it could be any shape, then the moment of inertia about the x-axis depended on the distance from the x-axis that the shape undertook. So how far was it from the x-axis? So the difference between moment of inertia and mass is the whole concept of position, the wheres. Go back to the idea of mass. One of the things that we talked about early on is that mass was another name for inertia, and Galileo described inertia as how difficult it was to change the motion of an object. But for mass moment of inertia, the idea is how difficult is it to change the rotational motion of an object. And what we'll see is that it's more difficult to change the rotational movement of, say, a bar where the weight of the bar is at the ends versus the same mass of bar where the majority of the weight is towards the middle. The distance from the majority of the weight from the axis of rotation is small in the second case, and so it's easier to change the motion of that bar. So in statics we had y squared dA, but you'll notice this is a length squared and dA is the area, so that's also a length squared. The difference between the moment of inertia that we talked about back in statics and the new mass moment of inertia is the fact that there is also the thickness of the plate, which still might be thin, but it's going to have some thickness, and then this density, where density by definition is mass per unit volume. So I can realign things. The volume is the thickness times the area. Okay, just imagine some arbitrary shaped plate. It has some area A and some thickness T. The volume of that plate then is the area times the thickness. And so density, volume density, is mass per unit volume. Or if I bring the dV over to the other side, then dm is rho times the thickness times dA. And that's going to help me figure out how to do these integrations. But this relationship that we learned back in statics is real important. So I know there's a moment of inertia around the x-axis. There's a moment of inertia around the y-axis. In order to find the moment of inertia around the z-axis, I add these two together. And I'm going to do that same thing even with mass moment of inertia. For the remainder of this course, when I refer to moment of inertia, I am really saying mass moment of inertia. Okay, so how are we going to find that? Well, let's consider a uniform thin ring. So we'll use a nice round ring, and it's thin, so this has some size, we'll call it dr. We'll keep it circular, not the best circle in the world, but there's some circle with radius r, and that's a constant, so let me actually call it big R. Alright, and it might have some thickness to it. Doesn't really matter if it does or not. So there's some thickness to that ring. And the way I'm going to do this, I know the moment of inertia about the center, so there's O. So I sub O is equal to the integral of r squared dm. So let's cut this into little sections. So there's a little section. Remember, this has got some thickness to it. And this little section is going to have some mass dm. And that little section is going to be a distance from the center of capital R. So that's one section. There's another section. It's also a distance of capital R, and it's got a small mass dm. What you'll notice is I go from the purple section to the blue section, and I could add in a red section, and it'll have some distance R and have some mass dm. What you'll notice is as I go from one dm to the next, to the next, to the next, all the way around, R is the same. It's constant. And since R is constant, it comes out of the integral. And it's equal to big R, and that's squared. It's coming out of the integral because it's constant. This is just the integral of dm. But what's the integral of dm? It's just the total mass. It's the total mass. Remember, an integration is a sum. So I add this mass plus this mass plus this mass all the way around this circle. And so that's going to give me m, we'll call that the total mass, r squared. Alright, so the integral of dm is the total mass, which I'll label capital M. That's the moment of inertia then of this uniform ring. Thin ring now, a thin ring. Okay, so let's consider the uniform thin bar. Bar is going to have some length L, and I'm going to rotate it about the center of mass. I'm going to call this the x-axis, the y-axis, and there's going to be some thickness in the z direction. Doesn't have to be rectangular in shape, but that'll work just as well. So we'll call that thickness in this direction T. then this is a uniform bar, so it's a uniform density. So that's mass per unit volume, which is length times height, which I'll call h. That'll be from here to there, times thickness. And then we're going to take just a little chunk of that bar, and it's going to have some thickness, dx, and it's going to be a distance x from the center of the bar, which is the axis of rotation. And it's going to have some mass, dm. So the moment of inertia is the integral of r squared dm, but r is the distance from the axis of rotation. So that's x squared dm. And I'm going to integrate across the entire mass. But now rho is equal to the derivative of mass with respect to volume, which is right here, but this is still true. And the volume of that little sliver is dx times h times the thickness t. And so dm is equal to rho ht dx. So when I substitute that into my integration, this becomes the integral of x squared rho ht dx. But rho h and t all come out, so it's rho ht x squared dx. And I'm integrating from over here, which is minus L over 2, to over here, which is L over 2. And so I0 equals rho ht x cubed over 3, evaluated from minus L over 2 to L over 2, which is rho ht over 3 L over 2 cubed minus L over 2 cubed. That's rho ht all over 3 times L over 8 plus L over 8. But this is 1 over 12 rho htl. But htl is volume. Rho times volume is mass. I'm missing a cube there and a cube there. So there's an L squared. And so I get 1 over 12 mass length squared. And that's the moment of inertia of a thin rod around its center of mass. Now if I have objects that are created by a lot of different objects, keep in mind an integral is a sum. So as I go to find the moment of inertia of a composite object, I have to consider adding it all together. One thing you want to do is beware of holes. Holes are objects of negative mass. Because basically how do you dig a hole? You take mass away. So these are objects of negative mass. So for example, if I wanted to know the moment of inertia of a plate with a hole in it, about, say, this moment of inertia, about that axis, it would be equal to, I would be equal to the moment of inertia of the rectangular plate minus the moment of inertia of the hole. The other thing we want to keep in mind is the parallel axis theorem. And this is very important, especially as I talk about that hole. Let's say I have a plate and I want to find the moment of inertia about the edge. How do I do that? Well, the center of mass is here. Okay, keep in mind the way you find the position of the center of mass is an integral again. It is a vector quantity, but it's an integral not of r squared, but of r, all divided by the total mass. So the moment of inertia about the center of mass, that I might know. It's in the back of the book. I can get it from there. Then the idea is that there's a distance between these two lines. The whole idea behind parallel axis is that this is an axis and this axis is parallel to it. I need to choose an axis parallel to another axis that going through the center of mass. They have to be parallel. And so if I know the moment of inertia through the center of mass, I just add m, the mass of the object, times d squared. Let's do an example that's not too hard. Think of a thin ring, and I'm going to rotate it around this point. So I'm going to rotate it, say, in that direction. Now there's an axis going in and out of the page right here. and this axis goes in and out of the page. So both of those axes are going in and out of the page, and they're separated by a distance that happens to be equal to the radius of the ring. Now we already know the moment of inertia, let's label this A, the moment of inertia about the center, which is C, so it's equal to IC plus MD squared. The moment of inertia about the center is mR squared. I did that earlier. And then the distance between C and A is R again, so mR squared. So the moment of inertia about A, if I want to take this ring and rotate it in this direction, that's going to be equal to 2mR squared. Okay, so here's a composite object. So to find the moment of inertia of this object, I'm not going to do the actual moment of inertia, but how do I do it? If I want to know the moment of inertia about L0, what I have to do is I have to break it into parts. So consider this semicircle right here, which is also this part right here. So I need to find the moment of inertia about this axis for the semicircle. Now that's going to require that I know the moment of inertia for a semicircle about its end. That information is in the back of the book. Then I'm going to find the moment of inertia of this rectangular plate about this point again, O, which is also this rectangular plate. So let's call it I of the plate, I of the semicircle, I of a semicircle over here. Now that's going to be different than this red semicircle because it's a farther distance. And it's going to require the parallel axis theorem. It's a farther distance from the center. Now this is only this portion right here. That's the purple portion. The yellow portion is going to be this circular disc. But keep in mind, I know what the moment of inertia is around its center. I'm going to have to use the parallel axis theorem again. And that's going to be, there's two of them, so we'll add them together. This one and this one. So plus I of the disk plus I of the semicircle, I of the semicircle on the right. This one would be on the left. And I'm going to add those all together once I've done those. We'll do some examples later.